Before we begin this lecture, let's talk about how we got here. We got here starting with business analysis that helped identify a problem to be solved and an application that needed to be built in order to solve that problem. Domain, problem, and solution analysis helped identify what was to be built. Through a requirements gathering process, requirements were captured about this system or application in terms of functional and non-functional requirements. Now the team has to design the system, starting from a high level. This high level design, if you will, is known as the architecture. So what is architecture? Architecture is an externally visible component, its structure, property, or its relationship with other externally visible components. So why do we make this notion of externally visible important? It is so that you can reason about how the system meets its requirements. In order to reason about a system, you have to look at things that are visible about it. Okay, certainly, and by the way, what do we mean by requirements? Certainly functional requirements, but more importantly, architecture is what determines how or whether a system meets non-functional requirements. Informally, you can think of architecture as the things that matter to the system, or the things that are hard to change about the system. So when it comes to software architecture, all that means is that the components, properties, and relationships are software components, software properties, and software relationships. All architectures are designed in the way they are designed because they're expected to meet goals. For software architectures, the goals are your standard non-functional requirements, performance, scalability, modifiability, etc. And of course, all the functional requirements as well. So for a university, the architecture has to meet the goal of educating students and doing research, which are the functional requirements, and also non-functional requirements such as educating students in 4 years to take a certain kind of job, to do research that would place the university in the top 25 of all universities, perhaps to do interdisciplinary research. All these are enabled by the architecture of the university. So all architectures, at least in order to understand them, but also in the way they are built, have components, and these components are sometimes called modules. They're sometimes called layers. Sometimes you have both modules and layers, where layers are specific partitions of the architecture, where the modules within a layer only talk to each other as opposed to across layers. Things like that. Anything that is big needs to be broken up into pieces in order to understand it. Architectures are usually important for things that are big, and that's why in order to understand them or describe them or design them or build them, you've got to build them in pieces. The next thing is that architectures need multiple views to describe it and understand it. So if you think about a university once again, a university has an organizational hierarchy consisting of departments that are composed into colleges that then get composed into universities. A university also has a physical hierarchy of classrooms and buildings. Both are views of the same architecture meaning the architecture of the university. Each is a view that describes some aspect of that architecture. Some aspect of that architecture that enables it to meet certain goals. So for example, the departmental hierarchy or the university's organizational hierarchy kind of describes how the department might do research or education. The physical structure of the university might describe how people get from one place to another when they go from one class to another. The second view is important to understanding how you might navigate the university from a physical perspective. The first view is important in order to understand how you might want to navigate the university from an educational perspective. The next thing you should know is that all architectures have static structure, things that don't change about the architecture, relationships that don't change about the architecture, attributes and properties that don't change about the architecture, and and dynamic behavior. So, for example, the structure of the buildings or the university's organizational hierarchy is an example of the static structure. But the way a student might, the way a particular student or a particular kind of student, say a computer science student, might get from one place to another in order to attend all his classes is part of his or her dynamic behavior. Um, Similarly, how a student progresses through his or her academic program is dynamic behavior. So anything that is related to process as opposed to physical structure may be thought of as dynamic behavior. Finally, all architectures have trade-offs. So for example, in the university, the hierarchy, the departmental hierarchy allows deep research in particular disciplinary areas. So you can do a lot of research in, say, physics and push the area of physics. But on the other hand, the departmental hierarchy makes it hard to address interdisciplinary problems. So if there's a problem that such as global warming that has social and cultural as well as technical issues, a university with its hierarchy, it makes it difficult to address that problem in a holistic manner. Similarly, for software systems, there are always trade-offs. So for example, there's always a trade-off between security and performance. So for example, if you use encryption to implement security with respect to data access, then you're going to slow down performance because you need to take you need to expend some computing in encrypting and decrypting the data every time it's stored or accessed. Similarly, there's a trade-off between security and usability. So you have to log in and provide your user ID and password and so on. You can't simply directly access the system and just use it. Since architectures have these kinds of things in common, you have common ways of defining, describing, creating, analyzing, evaluating, and documenting architectures. So you can use similar techniques across architectures, building architectures versus software architectures, to both design it as well as describe it, as well as analyze and evaluate it. We will look at two things that you do with architectures in this lecture. The first one will be how do you design an architecture, and then the second one is how do you evaluate and analyze and evaluate an architecture. Let's explore the notion of architectural views for a little bit. So architectural views can be categorized into three styles of views. Okay, the first kind of style is the module view, okay, which is basically how the architecture is structured or broken up as a set of implementation units. So you might think of a module view as describing some aspect of the static structure of the organization. Now remember, you can have multiple module views still. So when, coming back to the university example, the departmental college university hierarchy, as well as the classroom building road hierarchy, these were both module views, just describing different aspects of the university architecture. The second kind of architectural style, architectural view style, if you will, is the component and connector style. So here the idea is to show dynamic behavior and interactions between a set of elements in the architecture. The third style is the allocation view style. So here the allocation views describe how the software architecture relates to non-software structures, such as the hardware or the file system in the environment. Okay? So this tells you how the software elements are allocated, for example, to servers and other items in the hardware, or it might talk about how software components are allocated to files, essentially things outside the software system. Another way to look at architectural views is to try and understand what all views are necessary in order to describe an architecture. So Philippe Crucian from Rational Software Corporation came up with this 4+1 view model of software architecture. Basically said you need these 5 views to properly describe a software architecture. So in the middle is the use case view. So these are, which describes the functionality the architecture has to implement. Starting from the top left, the next view is the logical view, which describes the conceptual components of the architecture, as well as how that functionality might be implemented in that architecture at a conceptual level. So not at an implementation level, but at a conceptual level. So maybe you can think of your solution analysis diagram as something that belongs in the logical view. To the right of it is the development view. So this is how the system may be looked at from a programmer's perspective, and it's concerned with software management. This view is sometimes also known as the implementation view. Here you might talk about describing how the program files, the files with the code are how the code is broken up into files and stored on the file system. How you might build the system, how you might check out the system from SVN, things like that. Going down from there is the physical view, which talks about how the software components are mapped to the hardware, to the network, to servers, and so on. And to the left is the process view, which deals with the dynamic aspects of the system, explains the system processes and how they communicate, focusing on the runtime behavior of the system. In a complex system, this view is needed because you need to understand things like concurrency, distribution, how things are integrated, performance, scalability, things like that. So the last thing you should think about is how this 4+1 view relates to the architectural slides of the previous architecture styles of the previous slides. So essentially, you can use a variety of architectural view styles in each of these views. And one of the things you need to be thinking about in this class and also in the project is what diagrams or architectural styles you will use to represent each of these 5 views. So here's how you go about designing the architecture for a system. You essentially use a recursive decomposition process. So to begin with, start with a single module which represents the system. Essentially, you're beginning where solution analysis left off. Create a prioritization of the architecturally relevant requirements. In other words, those functional and non-functional requirements that will have the most impact on the architecture. So you basically want to look at the most complex use cases and the most complex non-functional requirements. By the way, you will find that the non-functional requirements are the ones that have most impact on the architecture. Start with the first most important requirement. Design the architecture using what are known as architectural tactics. You will see these architectural tactics in subsequent slides. Then take the next requirement and apply that towards designing the architecture, and the next one, and the next one, and so on. At some point, you will find that you need to break the system up into smaller modules with well-defined interfaces. So do that. And then once you have, at each step, at each iteration of this architecture design, verify the architecture using the use cases which define the functional requirements, and enhanced with quality scenarios. So not just use cases that describe what the system is supposed to do, but use cases that describe what the system is supposed to do plus how it is supposed to do it. So you should be able to log in, which is a functional requirement, within 5 seconds which is a non-functional requirement. And as you design this architecture, document this design using views. 4+1 views, and the diagrams that you will use there will be the diagrams corresponding to the different architectural view styles: module, component, connector, and so on. So what are these things called quality attributes? Quality attributes are measurable non-functional requirements. So non-functional requirements that you've been able to quantify in some way. So what are the things that define system quality? Well, it's the categories of non-functional requirements: availability, modifiability, scalability, performance, security, usability, testability, as well as business qualities. But then they are quantified. So you don't simply say the system must perform well, but you must say that for these use cases, the system must respond in 5 seconds. Things like that. You have seen examples of quantified non-functional requirements in earlier lectures, and you've also used them in your acceptance plan. So take the non-functional requirements, quantify them as quality attributes, prioritize them, and then apply them towards the architectural design. So let's talk about tactics for implementing quality attributes. Let's begin with availability tactics and then go through the list of all the other kinds of non-functional requirements. So for availability, you can categorize tactics into 3 categories: one for detecting faults, the second for recovery, and the third for prevention. So with respect to detecting faults, you basically have 3 approaches. One is that the component that is being managed periodically pings you and tells you, the manager of the component that needs to be available is periodically pinged by the manager to see if it's up. The second way is for the component that is being managed, the component that needs to be available, for it to periodically send a manager a heartbeat, a message basically saying that it is up and running. And the third approach is to do some kind of an exception mechanism. So you don't have to periodically ping the component, or you don't have it send you a message periodically, but rather if it dies, if something happens, an exception is raised and a message is sent to you at that time. Basically, the third one is a more efficient way of making sure that a manager is notified if the component that needs to be available goes down. The second category is for recovery, tactics for recovery. So with respect to availability, the usual tactic is some kind of redundancy. So having 2 database servers, or 2 web servers, or multiple web servers that you route requests to in some kind of manner. Or simply, if the system goes down, reboot it. By the way, redundancy can be active or passive. So you can have 2 databases that are both up at the same time, and every transaction is reflected in both databases. Or it could be passive, which is that only one database is actually getting updated. But if the system goes down, that database is transferred over to a second one and then brought back up as a replacement. The third category of availability tactics is for prevention. So one way of making sure a system is available and is doing the correct things is by using transactions. You would have seen transactions described in your database class. And another tactic for availability is demand management, which is prevent things like denial of service attacks, or prevent the system from being overloaded by only allowing a certain number of requests to go in at any given time. Looking at modifiability tactics, the general principle is the more you're able to localize and keep modular, the more you're able to modify later. So for example, if a search algorithm is localized into a particular class, well, then you can modify that search algorithm by simply modifying the class. Similarly, if all the data access related functionality is localized in a database, then by simply replicating the database, you can get scalability. The whole idea here with respect to modifiability is that you want to reduce coupling, which is the knowledge a component has with respect to another. Basically, any private knowledge that one component has of another component will reduce your ability to modify either of the components or to replicate either of the components. Um, and increase cohesion, which is the dual of coupling, which is the opposite of coupling. The idea is that each component does one thing well, and if you want to improve that one thing, or if you want to have multiple of that one thing in order to scale it, you can do so. The third category, the third kinds of tactics are for performance. And for performance, you essentially have the following tactics. You can either do things more efficiently, essentially reduce resource usage. You can reduce switching because switching has costs. You can simply add more resources, add more memory, add more, buy a bigger machine with more horsepower. Or you can do things in parallel. And just like with availability, another way of improving performance is by controlling demand, so that at least those requests that are in the pipeline of being processed, at least those will have good performance. So now let's talk about tactics for implementing other quality attributes. So let's start with usability. So tactics for implementing usability are, of two kinds. You can think of runtime usability tactics and design time usability tactics. With respect to runtime usability tactics, it is things like giving feedback to the user. So for example, when you save a file, and if the file is a large file, then putting up an hourglass or a progress bar to show that things are going on and that the system is not hung is a usability tactic that falls under the category of feedback. The other runtime usability tactic that human computer interface designers use are what are known as task models, user models, and system models. So they basically build these models of tasks and users and systems and use these models to understand how users will interact with the system, try to figure out how they might best interact with the system in the the quickest, most efficient way with the least number of clicks to achieve what they need to achieve. And they use these models to then design the system. There's also a tactic for design time usability, which is basically separating the UI into a separate set of components so that you can modify the user interface without changing anything with respect to the functionality, without changing the services that the system is supposed to provide. So now let's take a look at testability tactics. Remember that the goal of testability is the goal of testing, which is to show the presence of faults and not the absence of them, because that's not possible. So here are some tactics for implementing testability. One is being able to record all transactions that the system does and then be able to play them back. So many systems will use logs to output everything that the system does, and some systems will allow you to basically replay the log to make the system do exactly what it did earlier, just repeat what it did earlier by redoing what is there in the logs. Another testability tactic is stubbing out the interface from an implementation. So you can test everything around a component by simply accessing its interface while that component is under development. And the other way too, so if you're testing a component that requires another external component to be able to test it with, and that component is not available, then you can create a stub for that component and then test your main component, the component that you're building right now, against the stub of the other component. In many systems that access external services, so suppose you're building a PayPal-like system that charges your credit card and so on. In order to test PayPal, you can't start accessing credit cards during your testing process, because that would debit cards without purchases being actually made. So the idea here would be to create a stub of the credit card interface and link that into your PayPal system, so that you could simulate credit card payments being made without them being actually made. um, this idea is similar to the next one, which is this notion of specialized testing interface. But even those of you who have used JUnit will understand what I mean by specialized testing interface. So the idea here is to create a test harness that tests a component in all the ways that need to be tested. So it's not a complete application, it's just a small piece of an application that tests the component thoroughly. And then the final way is to use internal monitoring. So have enough logging within your system, have enough notifications within your system that you will be notified if something fails and what were the actions leading up to that failure, so that you can then figure out what went wrong and go back and fix it. You will see that the tactics for security are very similar to the tactics for availability. Now, these can be categorized into three kinds of tactics: for detection, resistance, and recovery. So with respect to detection, standard ways of implementing that are by monitoring access patterns and comparing them over time. So when you see anomalous access patterns, then you begin to suspect a security breach. You can do this in real time, or you can store large amounts of data and analyze it offline to figure out whether you've had a security breach in the past. The second category of tactics is around resistance. So basically prevention of security breaches. And the way you might do that, one is through authentication. So you have to log in or authenticate yourself before you have access. You have levels of authorization, so not everybody is allowed to do everything. So that exposure is limited by limiting access. Another tactic is encryption, basically protecting the data so that not everybody can read it, or rather an unauthorized person cannot read it even if they had access to it. And the last kind of tactic is through integrity preservation techniques. Things like checksums or parity bits. You might have seen this in your communication course to make sure that a packet has been has been received correctly. Things like that. The last set of tactics are basically recovery tactics. So all the availability tactics apply here, basically around redundancy. And the other tactic used here is using audit trails. So to basically identify who did what and when, so that potentially you can even roll back to get rid of a security problem. And also you have a trail that you can then use for investigation. So for identification of the problem first, and then investigation of the problem. What was done, who did it, and so on. An important process with respect to architecture is analyzing and validating architecture. So you might analyze or validate an architecture that you have designed, or you might analyze and validate an architecture that you have not designed. So for example, say a vendor comes to you with a certain system, you might want to analyze and validate its architecture. Or if you're buying a off-the-shelf product, you might want to analyze and validate its architecture before you put it to use. The techniques for all of these are common, and we will look at these techniques next. So an important component of any analysis or validation methodology are what are called scenarios. So the idea is that you create scenarios that have non-functional components in them. So do step X within 5 seconds, things like that. So the first step to any analysis or validation is the creation of these scenarios. And the scenarios are basically used to understand the non-functional requirements or the quality attributes of the system. These scenarios should cover a range of types of uses of the system. So anticipated uses of the system, which are called use case scenarios, or anticipated changes to the system, for example, growth scenarios, or unanticipated stresses to the system, like system crashes, denial of service attacks, things like that. The key thing to a good scenario is testability. So you have to know exactly what will cause that scenario and what what responses are of interest. So there is some way to, actually implement that scenario and test that the scenario has actually taken place. By the way, where have you seen this before? You've seen this before in your acceptance plan, okay, where you had to create these acceptance tests to make sure that that served as a contract between the customer and the developer of the system to make sure the system was performing as requested. A quick way of defining and documenting scenarios um, is by using what is known as a utility tree. So on the left, the utility tree is rooted at a node called utility. The first level of children are the standard categories of non-functional requirements or quality attributes. Performance, modifiability, availability, usability, security, testability, and so on. At the next level are basically categorizations of these further refinements of these categories. So for example, with respect to performance, this particular system had two categories of performance. One was data latency, the other was transaction throughput. With respect to modifiability, you had new product categories or the change of a off-the-shelf system purchased for use within that system, things like that. And at the leaf of this utility tree are the actual scenarios, labeled with a prioritization. Once again, the prioritization being a two component prioritization. The first component standing for importance, for criticality, and the second component standing for perhaps urgency. These scenarios are then used to pose architecture questions. So basically, the architect is presented with a scenario and then asks the question, how does your architecture meet this scenario? And the architect is supposed to give an answer, a precise answer on how his system meets that scenario. And you see an example of that on the slide. So when this architectural evaluation is done based on scenarios, these scenarios start bringing out questions that help analyze or validate the architecture at a deeper level. So if it's a performance scenario that is described, then the architect then explains how the architecture meets that scenario. The folks evaluating or analyzing the architecture can ask deeper questions. So when it comes to performance, they can say, so how are priorities assigned to processes? If the architect responds with, well, I have multiple processes that deal with these requests. The evaluator can ask, what are the message arrival rates? What are the expected transaction processing times? With respect to modifiability, the evaluator can ask, are there any places where the layers are broken? Is there any coupling between components? What components are connected not synchronously but asynchronously? So that there's actually more of an opportunity to be able to modify something or do some kind of delayed binding to that component. Things like that. So the goal of this architectural evaluation or architecture analysis is, of course, to see how, or whether the architecture meets the important functional and non-functional requirements. But it actually goes more than that. You want to understand also how the architecture, to what level the architecture meets the functional and non-functional requirements. So the idea is to basically identify in the architecture three kinds of things: sensitivity points, trade-off points, and risk points. So sensitivity points are the components of the architecture that are important to meeting a particular set of requirements. So what component or what property of the component enables the architecture to meet a requirement, that is known as a sensitivity point. So for example, a backup database is the sensitivity point for reliability or availability. The the degree of encryption is the sensitivity point with respect to security, things like that. The second kind of um items that you want to bring out through this architectural analysis are what are known as trade-off points. A trade-off point is a property or a component that affects more than one quality attribute. And in one case, it affects it positively. In one case, it affects it negatively. Okay. And finally, a risk point are those sensitivity or trade-off points which are close to the limit. So in case the load on the system increases beyond a certain amount, or the number of the number of users increases, whatever it might be, that component of the architecture is likely to be stressed beyond being able to meet its requirements. Those components or properties are known as risk points. So finally, we close with a slide that talks about the benefits of architecting, basically spending time designing the architecture before building the system. So there are two sets of lines here. The gray line shows the change to the schedule, the impact to the schedule because of doing architecture. And here, if you look if you look here, a large system of 1 million lines or more will have greatly reduced schedules if architecture is done, up to about if 50% of the time for the overall project is spent doing architecture. If more than 50% of the time is spent doing architecture for a large system, the time actually increases because you're spending too much time designing as opposed to doing the work. For a smaller system, about 25% of time spent on architecture gives you the best improvement to schedule. But for a small system, any time you spend on architecture essentially increases the time you would end up spending on the system. So if it's a small system and you have reasonably expert people, the recommendation is to just go ahead and build it, which, by the way, is the rationale behind Agile. Now, the second set of lines are the dark lines, which show added time added due to rework. So whether you have a large system, a small system, or a medium-sized system, if you do enough architecture, the time added because of rework, basically fixing things that you need to that you didn't fix the first time around, always drops to zero. Okay. For a large system, you might end up spending 100% of the time doing rework, 100% additional time doing rework. And if you did 50% of the time, if you spend it on architecture, you could get that down almost to zero. For a medium-sized system, you might spend 40% of the time, additional time doing rework, and you can get that down to zero as well, and so on for a small system too. So architecture is always beneficial because you're reducing the time due to rework. The real question that this slide tries to answer is how much overall time are you adding or reducing because of architecture? And basically it clearly shows that for large systems, doing up to 50% of the overall project time in architecture is beneficial. For smaller systems, you want to stay at around 25% of the overall project time and reserve the rest for building. For very small systems, don't spend too much time architecting. Just figure out your tools and your programming language and things like that, and then just go ahead and build it.